Welcome, we are continuing our discussion on Gauss eliminations. In this class, we will see some of the examples of Gauss elimination, which are some of the very critical examples in which the pivot terms become 0 and how to handle them. And then we will see how Gauss elimination can be expressed as a matrix operation, and we will try to look into another set of matrix solvers, which is called LU decomposition matrix solver techniques using Gauss elimination, which will come directly as an application of Gauss elimination. So, this is another example. One example we worked on in last class. This is another example, and this is the sets of equation x plus 2y is equal to minus 4z is equal to minus 3x plus 2y plus z is equal to 2, 3x plus y plus z is equal to 4. So, the first idea will be eliminating the first column from the second and third equation, which is x and 3x from second and third equation. So, we will subtract first equation from second equation, because they have same coefficient of x, and 3 times of second equation from the first equation. And the next equation that we will get is, interestingly, x plus 2y minus 4z is equal to 3, 5z is equal to 5, and minus 5y plus 13z is equal to 3. So, the y term of the second equation has already been vanished, because it is when we subtract second equation from first equation, it becomes 0. So, now we cannot subtract the coefficient of y is 0 here. So, we cannot subtract this from the third equation and subtract the y coefficient of the third equation. So, what we see here is that if I change my third equation and swap between second and third equation, we get a y coefficient of the second equation, which is important to have the pivot. So, this is a 0 y term coming on. So, we will interchange the equation, orders. And what we will get here is like this, which is already given us a triangular system, because x is eliminated from the second equation, y and z are eliminated from the third equation. So, forward substitution is in a way complete, and backward substitution will subsequently follow, in which I will eliminate z first and then I will eliminate y, and I will get equations for x, y and z independently. However, there is possibility of a case when this interchange is not possible, and we will see a case like this in the next slide, where we will call the break of elimination steps. These are the new sets of equation here, and we subtract first equation from the second equation, because the coefficient is 1 for x in both case, twice of the first equation from the third equation, and get the new sets of equation. So, we can see that the left hand side of the second equation is same with the left hand side of the third equation. So, they are in a sense linearly dependent on each other. So, if we subtract second equation from the third equation, we will see the last equation is getting 0 is equal to 2, which cannot be any equation. It is neither an equation nor an identity. So, this process essentially breaks here, because there is no way of interchanging the equation order, or there is no way in which we can find out z. So, this is what we will call getting a 0 pivot here, 0 pivot which cannot be replaced by rearranging the equation, the orders of the equations. So, and we will say that the process breaks here, row permutation. So, permutation between the equation will not work, and the process breaks here. Gauss elimination cannot work further, and of course, because these two equations are same, there is no unique solution of this equation, and we can actually check that there is no solution of this set of equations. So, Gauss elimination will break here. So, Gauss elimination works if there is any solution, any unique solution of this equation. If there is no unique solution, that means no solution or infinite solution, Gauss elimination will not work. For example, if this term would have been instead of 7, if this term is 5, that means this is minus 6. So, if this is minus 1, this term is 5, then this would have been 0 is equal to 0, and Gauss elimination, there is actually infinite solution, there are infinite solutions here, but Gauss elimination still would have been broken at this stage. So, it cannot move any further if we get a 0 pivot which is not eliminated by row permutation. Now, we will see what are the matrix operation equivalent of Gauss elimination. Instead of writing the equations, we will write it in matrix form and see what will happen there. And we will take the equation system that we considered in the second example, or the example we gave previous to that, where row permutation worked. So, this is the linear equation, and these are the Gauss elimination steps. First is the elimination step of x, and then there is a row equation permutation step of the second and third equation, which gives me the first forward elimination step. The equivalent matrix step is that this in the A matrix, the as well as in the B column vector, the first row and second row goes through certain steps, so that they are changed, and then there is an interchange of steps or permutation between second row and third row. So, this is a row combination operation for second and third row, and here there is a row permutation. Now, what is a row combination operation? Multiplying first, like subtracting first row from second row and multiplying first row by 3 and subtracting from third row. So, it is multiplying one row by some constant, it might be 1, it might be some constant which is non-zero, it might be 1, might be minus 1 if we add 2 rows, might be 3 something, and then subtracting it from another row. And we can see that this is written as multiplying the row 1 by L and subtracting it by row 2 can be represented by a matrix multiplication. If I multiply a matrix, any matrix A with this, then the first row of this matrix will be multiplied by the term L and subtracted from the second row. So, we can see this as the example. So, this matrix where it's firstly it's a initially it was an identity matrix, only the row that has to be multiplied by a particular quantity and subtracted from the next row. In the respective row column position, there is a term which has to be multiplied and subtracted, and if it is minus, then this is a subtraction process, if it is plus, then this is an addition process. So, inverse of subtraction is addition, and therefore, if I the inverse of this particular matrix is the addition matrix. So, if I subtract L times of first row from second row, I get this one. Now, if I add L times of first row with the second row in this matrix, I will go back to the original matrix. So, inverse of this is, instead of minus L, I have to write L, that will give me inverse of the multiplier matrix here. Similarly, there is a permutation matrix. If we are interchanging row 2 and 3, this will be the permutation matrix, where from the identity matrix the rows are also permutated. You can consider an identity matrix, we permutate the row, and we consider if I multiply that permutation matrix with the original matrix, it will get its rows permutated also. And inverse of the, so if I see, if I multiply this with this particular matrix, the row B and C will be permutated. Now, again if I multiply this with the permutation matrix, B and C will be again permutated, we will get back to the original matrix. So, inverse of permutation is the permutation matrix itself. If I take the permutation matrix and multiply it with the permutation matrix, I will get an identity matrix. Permutation matrix is itself its inverse. Now, we will look into the row operations that we performed in the last class and what are the equivalent matrix multipliers there. So, this is the matrix operation we did in the example 2, and we are subtracting first row from the second row, which is multiplying the original matrix by a row subtraction matrix, where -1 is in the position of first column in the second row. That means, first row will be multiplied by -1, first row will be multiplied by -1 and will be subtracted from the second row, where we will get that. The next steps is doing it for the third row will be multiplied, first row will be multiplied by 3 and subtracted from third row. So, this is the matrix we got from first row operation, then we multiply third row, then we multiply first row by -3 or first row by 3. So, this is in the first column of third row and subtract it from third row, and now we can multiply the multiplier matrices and get that this is the final matrix which will multiplied with A for getting this particular shape. And then there is a row permutation step, where we do a row permutation, that means we multiply this particular matrix by a row permutation matrix, and so this is finally the matrix that is multiplied with my A matrix, and it gives the resultant matrix, which is now an upper triangular matrix. So, there is a multiplier matrix which is multiplied with the original matrix A, and now we get the upper triangular form, and this is the form we aim to get at the end of the forward elimination step of the Gauss elimination process. And then there will be similarly multiplier matrix which will give me finally a diagonal form of A, from which we can directly solve. So, now we will see an important application of Gauss elimination. We have seen that Gauss elimination is a good method which elegantly can solve any equation system when there is a solution. However, it is restricted to the cases where there is no solution or there is infinite solution, but if there is unique solution, Gauss elimination can handle it. The next restriction on the Gauss elimination process comes to the fact that this has very large number of operations needed for cases where the matrix size is large enough. For example, for 10 to the power 6 into 10 to the power 6 case, it needs around 10 to the power 18 operations, which will take enormously huge time in even a very fast supercomputer. So, Gauss elimination is restricted usually to smaller matrices even when we are using computer program, but there is a variant of Gauss elimination which can probably work better for certain matrices and even can be taken forward to solve large matrix systems. For that, we will look into an application of Gauss elimination which is called LU decomposition. So, if we see what are the matrix operation performed during row combination, we have seen that multiplying first row by L and subtracting from 2 needs a multiplication with a matrix like 1 0 0 minus L 1 0 0 0 1. So, with the row which has to be multiplied by L and subtracted from that particular row in the same row column position or column row position, this is multiplied, L will be multiplied with first row at A matrix and subtracted from second row in the first column second row position minus L will be there, and this we have seen earlier. So, if we think of successive row operations, and which we actually do in a Gauss elimination process, that the row operation multiplying one row by one particular constant and subtracting it from other, we do it for several times. So, we do it for one particular row, we again do this is L times of row 1 subtracted from row 2, and then in Gauss elimination what we will do, we will also multiply something with first row and subtract from the third row. So, m times of row 1 is subtracted from row 3 will be a process like this, and in Gauss elimination ideally I should get these two terms to be vanished. Now, the next step will be that you multiply something with this row and subtract from the third row. So, which is like, so this is what you get after the first row operation, like these two are the multipliers, and the third operation is and if we multiply them, because these are independent operations on each row, they kind of add up, the multiplication matrix adds up, and you can try it yourself, you will see that this is the product of the multiplier matrices here. The next step will be n times of row 2, like row 2 has to be multiplied with something and and subtracted from row 3. So, n times of row 2, which is the modified row 2, is subtracted from n 3, but modified row 2 is modified by as the terms of row 1 is added to them, and row 3 is also modified. So, this will be with the new matrix you use a multiplier matrix and you get this particular term. So, if I see what is the final multiplier matrix, that is multiplication of these two matrices, and this is a matrix like this. Interestingly, when we carry on these operations, first which is like a Gauss elimination operation, we multiply something with first row subtract from second row, we multiply something with first row subtract from third row, we multiply something from and so on, then we multiply something with second row subtract from third row and so on. So, we carry out these operations, we get a lower triangular multiplier matrix. This matrix has a lower triangular form. So, successive elimination steps is in Gauss elimination is equivalent to multiplying the main matrix by a lower triangular matrix. And we have seen that inverse, and now we will see what is the inverse of that actually. An inverse of a multiplication matrix, which is a row operation multiplication matrix, is only you substitute the negative off diagonal term by a positive off diagonal term, but this is for single step multiplier, not for the final multiplier matrix. Now, let us consider Gauss elimination of a 3 by 3 system A x is equal to b, and we get this particular matrix equation. We subtract twice of the first equation from the second equation, which is multiplying by this particular matrix. The next step is, and we get a final matrix like this, a new matrix like this matrix equation. Note that b vector is also changing during these steps. The next step is adding the first equation with the third. So, with this particular matrix, which is a new matrix, now I added the first equation with the third, and this is the multiplier matrix, we get a matrix like this. The next step will be add the second equation with the third, and we multiply it with another matrix, and we get this particular matrix form. So, now we can finally write that A x is equal to b, which was my initial matrix equation, is changed to u x is equal to c, where u is an upper triangular matrix. A is multiplied with certain matrices. We have earlier seen, this is important, that this is a lower triangular matrix which is multiplied of A to give me u, but u is an upper triangular matrix. So, and then if we get this, then we will do certain back substitution terms to get a diagonal matrix. However, we can see that this matrix u is few matrices multiplied with A, or if I write it down. So, we can say that u is a row operated form of A, and we can say that U is equal to something into A, and that multiplier is a lower triangular form. There is a lower triangular matrix which is multiplied with A gives me an upper triangular matrix. U is an upper triangular. So, we get that upper triangular shape by multiplying some row operation matrix with A, and the final row operation matrix is of lower triangular shape. If, and this is done when there is no row permutation will gives me something different result, but let's look into this case only first. So, this is what we got. A is the lower triangular matrix multiplied with U is the lower triangular matrix multiplied with A, U is itself our triangular form, and we can write A is equal to inverse of this matrix into U. And further, these are the matrices which have been multiplied to U. So, it is like U is equal to matrix E multiplied with matrix F multiplied with matrix G into A. So, I can write A is equal to G inverse, F inverse, E inverse, U. We are using the property that as A B inverse is equal to B inverse into A inverse. We are using this property. So, if I write that U is equal to inverse of this matrix. Now, this is very easy to invert this matrix, minus 2 will be plus 2, we will get the inverse. This one will be, all the off diagonal terms will change their sign, this one will be minus 1, I will get an inverse, this one will be minus 1, I will get an inverse. So, I can write that this is the inverted form of the matrix, and if we multiply them we get another lower triangular matrix here. So, this is a lower triangular matrix. So, what we are seeing here, that A comes as a multiplication of the lower triangular matrix, which is inverse of the matrices needed for Gauss elimination step and the product of inverse of the matrices, and the U which is the matrix after the forward substitutions, all the forward substitution steps of Gauss elimination is over, or which is an upper triangular matrix. So, we can write A is equal to a lower triangular matrix into upper triangular matrix, or A is equal to LU, where L is a lower triangular matrix and U is an upper triangular matrix. Gauss elimination steps are the steps through which I am getting U finally, and this is the inverse of this matrices is giving me, the multiplier matrices with A is giving me L. So, L and U are very unique with Gauss elimination, and as Gauss elimination is kind of a direct process, there is only one Gauss elimination process possible for one particular A matrix, then LU decomposition is also unique for any matrix. There is only one particular combination of L and U which can be obtained for a square matrix through Gauss elimination. That is, for any matrix A, only one Gauss elimination process, there is only one unique Gauss elimination process, and that will give an unique upper triangular matrix U, and this unique Gauss elimination process will give me an unique L also. This gives me an unique L also. So, if I write A is equal to LU, or when we can do that decomposition A is equal to LU, there is only one L and U for a particular full rank matrix. There is only one lower triangular matrix and only one upper triangular matrix whose product can be written as A is equal to LU. For any A, this factorization is unique, there is no other possible combination for any particular matrix A. Now, this LU decomposition can be taken one step forward, and this is important that this LU decomposition is unique to any matrix A. If the matrix can be solved using Gauss elimination, there will be only one LU decomposition possible. Now, this LU decomposition can be taken one step further, which is U can be finally further decomposed as a diagonal matrix and another upper triangular matrix. So, we take D1 out of it and divide all the terms of the first column by D1. We take D2 out of it and divide all the terms of the second row by D2. So, first row, second row, so on. So, and this is possible because the pivots are non-zero. These are basically the pivots, non-zero pivots of U. If any of this pivot is 0, the process would have stopped here. So, we can then write U is a combination, or U prime. If this is the particular matrix U prime, we can write U prime is a multiplication of a diagonal matrix and another upper triangular matrix. So, upper triangular matrix can be split further decomposed into a diagonal matrix and an upper triangular matrix, and then we can write A is equal to LU prime, or A is equal to LDU. Instead of LU decomposition, we can also have a LDU decomposition. Note that this U will be different than U prime. So, this is also a unique decomposition of any A matrix. A can be written as LDU also, and D is the diagonal matrix of pivots, and D there is no 0 element in the diagonal of D. D has to be non-zero, or pivots have to be non-zero here. So, this is how Gauss elimination can decompose an A matrix into LU matrices or LDU matrices. Now, there are certain advantages of LU and LDU decomposition, and they can be utilized in several purposes using solving of the matrix equations, and these solutions are usually faster and simpler than the standard Gauss elimination process. And also, apart from Gauss elimination, there are some other applications of LU decomposition also. Some we will see in the next class, and some of the applications of LU decomposition will come at the later stage of this course, when we will look into iterative solvers, which is not like directly solving x is equal to b, going through certain iterations starting from a guess value, and how the iterative solvers can be speeded up. We will see that LU decomposition will come something like a preconditioner, which will increase the speed of the convergence of iterative solvers later. But in next class, we will see some interesting utilization of LU decomposition for solving Gauss solving matrix system, as well as for finding determinants or for finding inverse of one particular matrix. Thank you.